Now that you've been introduced to a little bit of what simple harmonic motion is, I want to talk about what types of equations are used to actually represent simple harmonic motion. Let's take a look at this picture of the ball that's oscillating on a spring upwards and downwards. We learned in the previous video that equilibrium is when displacement or distance is 0. So let's draw a horizontal axis through our equilibrium, and let's, through that, on the left-hand side, draw a y-axis. All right, so if I were to trace the pathway of this ball on the end of the spring, or the weight on the end of the spring, from equilibrium to its maximum negative displacement, back to equilibrium, its maximum positive displacement, and then back to equilibrium. So assume that here is where this is all one spring and it's going down, or it's at equilibrium, it's falling, it's starting to go back up. At this point it's at its maximum, and then it's coming back down to equilibrium. So you can see that this blue pathway looks like a sine curve. So sine is one type of function which we can use to model simple harmonic motion. Now look at the red spring. Let's assume that rather than the spring starting at equilibrium, it starts at its maximum positive displacement. And as it falls, it will cross over the point of equilibrium to its maximum negative displacement. It'll cross back over its point of equilibrium, and finally its point of maximum positive displacement. And you can see this red function is indicative of a cosine function. So sine and cosine can both be used to model simple harmonic motion. Now also, let's think about, as this spring is rising and falling, time is passing. So with simple harmonic motion, while the vertical axis represents your displacement, your horizontal axis represents time. So our equations for simple harmonic motion are written as d, displacement, is equivalent to a for our amplitude, times the sine of omega t, or d equals a times the cosine of omega t. A still corresponds to the amplitude, omega corresponds to b, the coefficient of x, and t corresponds to time. So rather than having an angle along your x-axis, time will be represented along the x-axis. So simple harmonic motion is represented as displacement as a function of time, and I should say vertical displacement as a function of time. So we now understand the types of equations that are used. The vertical distance represents our displacement, and the horizontal distance represents time. So next let's talk about, well, how do we know when an equation models the sine or the cosine wave? Or how do we know if the actual motion shows a sine or a cosine wave? If the function begins at its maximum or minimum displacement, then it's a cosine wave. We know that cosine always begins at the amplitude. So if the simple harmonic motion begins at the maximum or minimum displacement, it will be represented by a cosine wave. If the function begins at equilibrium, it will be represented by a sine wave. And then lastly, how do we know if A is positive or negative? Well, if we look at this picture in blue of the sine wave, we can see that while we're starting at equilibrium, the spring is going downward first. So in that case, A would be negative. If we look at the red, where cosine began, it began at its maximum. This case, A would be positive. So you would have to interpret that through the equation or the given information. Let's practice a few examples of writing equations. So an object is attached to a coiled spring, like in the picture we saw, and it says the object is pulled down, then released. Important to note it's pulled down and then released. Write an equation for the distance, that's d, of the object from its rest position after t seconds. So write an equation for the distance of the object from its rest position after t seconds. And I should note, let's go back and look at one thing. The origin time would represent 0 seconds. All right, let's look at example 1. It says the distance from rest position at t equals 0. So for number 1, I'm just going to draw a simple sketch to help us understand the equation better. The distance from the rest position at t equals 0, or the displacement from the rest position, is 9 centimeters. So if the rest position is at the origin at t equals 0 seconds, our coiled spring rests at 9 centimeters. Notice that our amplitude is also 9 centimeters. So we know that the function is starting at the maximum positive displacement. Because it's starting at the maximum positive displacement, I know that my equation is going to be a cosine function. Okay, let's continue. The period is 10 seconds in length. So I know that it should go through a full cycle of cosine in 10 seconds. Let's use this to write our equation. So d is equal to, remember A comes from our amplitude, and because we're starting at positive 9 centimeters before it's pulled down, A will be positive 9. Cosine of omega times t. All right, well, remember that omega is just replacing b. As you recall, the formula for period is 2 pi divided by b. So in terms of simple harmonic motion, the formula for period is 2 pi divided by omega. So we can replace p with 10. 10 seconds is equal to 2 pi divided by omega. And we can now multiply by w. And then divide by 10. So 2 pi divided by 10 is pi over 5. So our equation is d equals 9 cosine of pi over 5t. Let's take a look at example number 2. In example 2, we're told that our distance from rest at position time equals 0 is 0. So that lets me know that I am starting at 0 seconds. My vertical displacement is 0. It hasn't started from above or below, but at equilibrium. Remember, 0 is equilibrium. I'm told that the amplitude is 4 and the period is 3.5 seconds. So if the amplitude is 4, that gives me my maximum positive and negative displacement. And if the time is 3.5 seconds, I can now draw a sketch. Remember, the object is pulled down and then released. So we would go down and then through the rest of the curve. So when I look at this, I know that if my amplitude's 4, but it's pulled down from equilibrium, A is negative 4 times the cosine of omega t. The period is 3.5 seconds. So again, if we cross multiply and solve here, we would have 3.5 omega equals 2 pi, and then divide both sides by 3.5. And 2 pi divided by 3.5 comes out to be 4 pi over 7. And now we've been able to write two equations that model simple harmonic motion.